Hello and welcome to another video for pre-calculus. In this video, we are going to discuss about some application of exponential functions. There are so many applications, we cannot present all of that in one video, but I'm just going to look at maybe two or three examples which has the basic concept and application of these exponential functions. So the first application is we use exponential function as a growth function. So in order to model a population growth, we use an exponential function. So as the equation for that population growth, so P of t means the current population or the future population or the population after time t equals P naught, which is the initial population, or at time t equals 0 times e to the k times t, where k is the exponential growth rate. There is a relationship between the growth rate and doubling time. So when we say doubling time, it is the time required to double the population. So for example, if we start with 10,000 population, the time that it requires to make that population 20,000 is the doubling time whenever the population gets double. So there's a relationship between the growth rate and the doubling time. So it's given by, so K times T means growth rate times time, doubling time equals natural log of 2. Or if we want to find the growth rate, then we can divide natural log of 2 by the doubling time. Or if we want the doubling time and if we know the growth rate, then we can do natural log of 2 over growth rate. Okay, so that gives us the doubling time. Now let's look at an example. Here's an example of population growth. So in a certain country, the population in 2015 is 27.3 million. Okay, so right here. And then it has an exponential growth rate of 2.2% per year. Now we are asked to find the function representing this population growth. So let's go ahead and write that one down. So we'll use the growth function, so which is P of t equals P naught e to the kt. Now, we need a couple of things here. We need the initial population. We have that. So P naught is 2.27.0. Okay. And then we have K, which is the growth rate, which is 2.2, but we will change that into decimal. So K equals 0.022. So if we put this down here, then the function that represents this population growth is P of t equals 27.3 e to the 0.022 t, and this will give us the population after time t in millions. Okay, so let's look at the part B of that question. So it says estimate the population in 2022. That means this function consider the population in 2015 as the initial population. So 2022 means that is after 7 years. So what we are going to find here is we are going to find P of 7 equals 27.3 e to the 0.022 times 7. And we can put the whole thing into the calculator. And then if we do that, that gives us 31, approximately, okay, 31.85 millions. So that means in 2022, the population with the same, with that exponential growth rate can be projected at 31.85 millions, okay? Now let's look at the next part of this question, part C, which is asking us to find after how long will the population be double when it was in 2015. So in 2015 it was 27.3. Now we need to find when is that population going to be double, or when is that going to be um, double of what we have in 2015. So now we'll just use the doubling time formula, which is right here. We discussed that. So t equals natural log of 2 over k. So t, or the doubling time, t equals natural log of 2 over k. Natural log of 2 over k here is 0.022. And then if we put that into the calculator, we will get t equals 31.5 approximately. So The population is going to be double after 31 and a half years, okay? Or approximately we can, if we round that to the nearest year, then we can say after 32 years. Now let's look at the part D of that question. So the part D is asking at this growth rate, when will the population be 50 million? Now we need to find the time. So again, we'll use this function, which is P of t equals 27.3 e to the 0.022t. So we are finding time now. We are given the future population, which is 50, equals 27.3 e to the 0.022t. Now we have to solve this exponential equation. So first we are going to divide by this one, 27.3 on both sides. Okay, so when we do that, we get e to the e to the 0. Let's erase this. So this gives us e to the 0.022t equals, let's just write that as 50 over 27.3. Let's not divide, because if we divide and round that now, we might not get more accurate answer. So we'll just leave that as a fraction. Now, in order to solve this one, we know that we did the exponential equation in the previous video. So we'll just take natural log on both sides. So when we do that, the left hand side becomes, so we use the power rule and that comes down here. So 0.022t natural log of e equals natural log of 50 divided by 27.3. Now divide, if we, so we know that natural log of 2, natural log of e, this quantity right here, this is 1. So that gives us 0.022t equals that one. So in order to find t, we have to divide by 0.022 on both sides. So if we do that, and if we put this right hand side into the calculator, we'll get t equals, so this is approximately, okay, so it's approximately 27.5 years. Or we can also round it to the nearest year, so which means we can say this is approximately 28 years. So the population is going to be 50 million after 28 years, or since we are counting from 2015, so this means in 2043, the population is going to be 50 million with that exponential growth rate. Now, another application of exponential function is exponential decay function. So the previous one was growth when something increases. Now, if something is declining or decreasing, then we use the decay function, okay? Again, the formula or the function is same as the previous one, except for the decay, we have this negative sign here. So P naught represents the initial population, K is the exponential decay rate now, it's not growth rate, and then t is the time, p of t is the future or the present population or population after time t. So yeah, that's the formula that we are going to use. Now, just like doubling time, in the growth, we have a half-life when it's decaying. So it's exactly same as the doubling time. So here it's decreasing. So half-life is the time it requires to reduce the population or the amount, whatever is declining, to a half of what we start with. So for example, if we are talking about radioactive materials or radioactive elements, and then if we start with, for example, 10 grams, and then it's decaying, so the time it takes to become 5 gram is the half-life, okay? So again, this half-life and decay rate has the relationships similar to the growth rate and the doubling time. So K times T equals natural log of 2, and to find K, we'll use this one. To find half-life, this T represents half-life here, we use this formula. So let's look at an example. So a wooden artifact contains 70% of carbon 14. So 70% of carbon 14 that is present in the living trees. How long ago to the nearest year was the artifact made if the half-life of carbon 14 is 5,750? So first, let's go ahead and write the decay function. Okay, so decay function is P of t equals P naught e to the negative kt. Now we know that 70% is present now. When something is given in percentage, we consider the initial or the starting amount as 100%. Okay, so we say this is 70% equals P naught is 100% because that's the initial or the beginning when we consider something in percentage. Okay, so e to the negative, we want k and we want t, so we don't have both. But what we can do is we can use this half-life to find the value of k. Okay, so we'll use the half-life formula to find the value of k. So k, we know that k equals natural log of 2 divided by half-life, which is 5750. And if you put this into the calculator, you'll get 0.0001255. Okay, now let's put this into our function and then we can find t. So here k is 0.0001255. There are more decimal places, but I'm just rounding and leaving it over there. If you want more accurate answer, you can just use this fraction instead of using the decimal in place of k. Okay, times t. So that is the function. Now we are trying to solve for t. That gives us the age of that artifact. So we are going to divide by 100 on both sides. So divide by 100. And that gives us, okay, so let's write that exponential part on the left hand side. So e to the negative 0.0001255t equals 0.7. Now we'll take natural log on both sides. So we'll take the natural log on both sides. Now when we take the natural log, this exponent comes to the front. So we'll have negative 0.0001255 t natural log of e equals natural log of 0.7. Again, we know that natural log of e, this one is 1. So that gives us negative 0.0001255t equals natural log of 0.7. And then if we divide by negative 0.0001255 on both sides, that will give us, so let's put this into the calculator. So when we put this into the calculator, we'll get approximately, okay, so this is an approximate, so 2958.73. So we can say approximately that artifact is 2959 years old. Let's look at one more example. So a vectorial culture has an initial population of 10,000. Okay, if the population declines, it's decreasing to 4,000 in 8 hours. What will it be at the end of 10 hours? Assume that the population decreases according to the exponential model. Okay, so again, we have to use the decay formula here. So P of t equals P naught e to the negative kt. Now the initial population is 10,000, so P naught is 10,000 e to the negative, we don't have k, but we have that it says in 8 hours the population is 4,000, so we put time equals 8 and the population equals 4,000. So this will help us to find k. Once we get k, we'll write the function and then we'll calculate for 10 hours. Okay, so that's how we are going to proceed with this problem. So now, if we divide by 10,000 on both sides, okay, so let's go ahead and divide by 10,000. So we'll get e to the negative 8k equals, so if we divide by 10,000 on both sides, we get 2/5. Okay, now take natural log on both sides. So if we do that, we get negative 8k and times natural log of e equals natural log of 2/5. And then natural log of e is 1, so this is just negative 8k equals natural log of 2/5. Then divide by negative 8, we get k equals natural log of 2/5 over negative 8, so we can put negative right here. Okay, so that's the k. Now what we do is we'll put this into our function. So p of t equals P naught e to the so we have negative in K and we have negative in the formula, so this becomes natural log of 2/5 over 8 T. So this quantity will become negative, okay, if we put it into the calculator. I'm not just putting it into the calculator to get exact, but yeah, if we want, we can put this into the calculator. Let's do that. So if we put this into the calculator, this is what we are going to get. So we are going to get K equals, so if we put this into the calculator, you get 0.114536. Okay, so let's write the function P of t equals P naught e to the negative, so K is 0.114536 times t. So that is the function or the model that represents this decay. Now our question is, what is the population of the bacteria after 10 hours? So what we are going to do is, to answer that question, we are going to find P of 10, or that equals P of 10 equals, so P naught is not going to change, so it is 10,000 e to the negative 0.114536 times t is 10. Now if we put the whole thing into the calculator, we are going to get approximately, so that's an approximation, we are going to get 3,181. Okay, so that is the number of bacteria, or the bacteria population at the end of 10 hours. So there are so many applications of logarithms as well. So two main applications that I just want to put it here. The pH scale. So if you are in chemistry class, you have seen this before. So, and the other one is the Richter scale. So pH scale is used to measure the acidity of certain solution, okay, any solution. So where pH equals log of H positive, where H positive is the hydrogen concentration, okay, in a solution. Now the pH scale ranges from 0 to 14. So if the pH is 7, then it's a neutral solution. Like pure water is a neutral solution. It's not neither acidic nor basic. So the pH of pure water should be 7. Okay. Um, then it is acidic if the pH value is less than 7 and it becomes smaller and smaller, gets closer to 0, it becomes more and more acidic. And similarly, if it is greater than 7, then it is basic. And when it increases, it becomes more and more basic. Similarly, the other use of log is uh, we use a scale which is called Richter scale that we use to measure the intensity or the how severe an earthquake is. Okay, so this is how we measure it. So this is how we measure it right here. This is the formula. Now there's a threshold which is I naught. That's, I think it's used as a threshold because that's the minimum intensity that the seismograph or the scale, whatever that machine that they use to measure this one can capture. Okay, so the interpretation of these Richter scale numbers are, so for example, if we have an earthquake of 6 Richter scale and 7 and 8 Richter scale, so this 7 Richter scale earthquake in the Richter scale is one more than this one, right? But in terms of interpretation, we say this is 10 times, okay, this is 10 times intense than this 6 Richter scale earthquake. And if we move on to 8, if it is like 2 more, then that is 100 times. If it is 3 more, that's 1,000 times intense than what we have. Okay, so that's how we use this log to measure Richter scale. So these are some applications. There are so many other applications. As I said earlier, we cannot discuss that in one video, but I showed you some examples. And we'll just stop here for this video.